All right, folks, what we want to do today is we want to define density, perform a density calculation, and as we're looking at density, we actually want to look at the variables that make this up and then try to figure out whether they're extensive or intensive properties. All right, so the question is, what weighs more, a ton of bricks or a ton of cotton? Well, this is a trick question. They both weigh the same, but if we start to think about this, where people might be misled is they're actually thinking about density if you were to answer bricks, okay? Because the bricks will be more dense than the cotton. So whenever we start to calculate density, which we'll use a capital D for density, or sometimes you'll see a rho, but density is equal to mass over volume. Typically this is going to be measured in terms of grams per milliliter or kilograms per liter in this class. But as we start to look at this and start to consider some of the different variables, we have mass, volume, and density. So if you recall, extensive properties depend on the amount present. Okay, so extensive properties depend on the amount present. And what are some examples of variables like this? Well, we have volume, we have mass, we have length, and we have something that we haven't talked about yet, but it's known as the heat capacity. These are some examples of extensive properties. But notice that density isn't listed here. Okay, so if mass and volume are extensive properties, surely density is an extensive property as well. Well, not really. Density is actually an intensive property, which means that it is independent of the amount present. So like I said, examples of this would be density, temperature, or the specific heat, which we'll compare to the heat capacity in a much later unit. So how can this be? How can we get an intensive property calculated from two extensive properties? Well, I want you to consider an example. Let's consider a glass of water versus a pond filled with water versus a whole ocean full of water. Okay, so what we'll find out in a glass of water versus a pond versus an ocean, the amount of water varies. Okay, shouldn't be surprising there. But what we could say is if this was pure water in the glass, the pond, and the ocean, so if we ignore solutes such as salt, what we'll see is the density of water is the same. If the density was extensive and it depended on how much water was present, then a person should be able to walk across an ocean. But because this is not the case, because the density is intensive, this means that someone cannot walk across the ocean. So it's just the water from the ocean has the same density as the pond and the glass. So let's go ahead and try to use this equation, D equals m over v, for our density, to solve for the density in a problem. All right, so a couple things before we start on this problem. One thing is you must know this conversion. 1 cubic centimeter is equal to 1 milliliter. Okay, and that will be used throughout this entire course. And then we also need to come up with a set of general steps for solving a problem. So, the first step will be list your variables. The second step will be to write your equation. which we can usually figure out which equation to use based off of which variables we have and what we're asked to solve for. The third step will be solve for the unknown. And then your fourth step will be to convert any units that you need to. And finally, the fifth step be plug and chug. So plug in your numbers and then put it in your calculator. So in this example, we have a copper block occupies a volume of 10 liters. How many pounds does this block weigh? And then we're given a couple things. So recall that this rho stands for the density. So density of copper is equal to 8.94 grams per centimeter cubed. And we also have the conversion factor that 1 kilogram is equal to 2.20 pounds. So the first step is let's make a list of our variables. Okay, so we're looking for pounds, so we're going to relate the mass to that. So we don't know the mass. We do know the volume. The volume is 10 liters. We'll talk more in a later lecture why I have 10 with the decimal point and why that digit is significant. Then we're also given the density of copper to be 8.94 grams per cubic centimeter. Okay, so now what we can do is we can go ahead and write our equation out because, well, right now the only equation that we've talked about is for density. So D is equal to M over V. Well, we're trying to solve for mass, so let's rearrange our equation to solve for the mass. So in order to do that, what we'll do is we'll multiply both sides by V. So the volume will cancel out on the right-hand side, and we will end up with mass is equal to density times volume. All right, so we're going to plug in for density and volume, but one of the things that we should take note of is in the density, it's grams per centimeter cubed, and in the volume, it's in liters. So what we should probably do is we should convert those liters to milliliters, and then consider changing that to cubic centimeters. So here, we're going to convert liters to milliliters, just like any other conversion. We're trying to cancel out the liters. So liters will go in the denominator, milliliters will go up top. So we put our 1 with the prefix, 10 to the negative third with our base unit, and our liters will cancel out, and we will be left with 1.0 times 10 to the fourth milliliters. Since we said that 1 cubic centimeter is equal to 1 milliliter, we could go through and just multiply by 1. So 1 cubic centimeter per 1 milliliter. Milliliters cancel, and we end up with the same answer, which is 1.0 times 10 to the fourth cubic centimeters. And so now we should be ready to plug into our equation because we've converted our units. So plugging in for the density, we have 8.94 grams per cubic centimeter. And then we have our volume, which is 1.0 times 10 to the fourth cubic centimeters. The cubic centimeters cancel out. And then we end up with our mass being 8.94 times 10 to the fourth grams. So we're almost there because this problem is actually asking us to figure out how many pounds. Well, how can we go to pounds? I give you the conversion from metric to English up here, kilograms to pounds, but our answer is currently in grams. So that means we're going to have to take our grams and convert that to kilograms. So we will have 1 kilogram up top, 10 to the third or 1,000 grams in the denominator. So our grams cancel out. We're left with kilograms. And finally, we can go through and multiply by our conversion factor, the 2.20 pounds per 1 kilogram. Upon doing this, you'll get the answer of 196.68 pounds. But considering sig figs, we're going to have to round this. So in a future lecture, what we'll find out is we can only have 2 significant digits. So whenever we try to round this to 200 pounds, we'll see that sig figs are an issue. So this will actually end up being written as 2.0 times 10 to the second pounds. But we will address the significant figures issue in a coming lecture. So right now, the key point would be that you got to the point where you had 197 pounds, or the 8.94 times 10 to the 4th grams.